Hello, this is the recording for the supplements to the class we did on last Thursday, that is 11th of November. That time our connection to the computer internet wasn't very good, and frequently my voice wasn't properly transmitted, and the screen did not change. The PowerPoint screen doesn't show up properly. So I decided to make a recording up to the point that we covered last Thursday. So I want you this part to be just a review, or in a way the makeup of those previous sessions, and all the rest of the coverage of this PowerPoint slide is in separate file. So you can either skip this one or go ahead and try to understand it. Okay, so here this chapter, this PowerPoint is about feature detection and matching. Of the chapter 4, we have covered 3 subjects in terms of PowerPoints. So I made 4A. That was edge detection, so it's more like how to know those boundary and the edges. And then 4B was exclusively about half transformation, and then this one, the feature detection and the matching, is under the title of 4C. So you can find the PowerPoint files corresponding to those subjects like 4A, 4B, and 4C. So today's subject is a feature detection. Of course, the feature, what does that mean? So feature is actually, when you look at the dictionary, that is something of a characteristics or something important or significant. I give you the too many the words, and then maybe confusing you even more. But something, when you look at the picture, something you are watching, or something worth looking in. So let's give this example. Here's some scenery, a little small, so it's harder to see, but the list that bear with me. So there's some mountain, rocks, and there's some bush, something, and here's some tower. So we don't know what is the important, but in understanding this picture, what this image, as you know that computer vision is let the machine understand the scene or the picture's meaning. So here what we can easily think about is, oh, these 2 big towers are something of interesting or important or worthwhile that characterize this picture, main point of this picture. So we can say that all those terms of that's something important, something worthwhile, something significant, that is a feature. So let's detect it. So in this simplified, more like the edge detection, or this, the thinning the picture, we see some sign of 2 towers and some mountain and some trees, something like that. Then in here we have some kind of animal or something we don't identify yet. So at this stage of computer vision, that we are just isolating out. So out of those all backgrounds and the many things that is shown or existing in the picture, we are just focusing on something very important. The same thing was here. So here some cat or the tiger or whatever that is on the tree, and the other main tree branches, that's something we may be paying attention to. And here's some rock that is worth noting. So that is the idea about our features. So soon you will know that when the computer system software trying to figure out or detect the features, then they are usually go in point like that one, those corner points, or some kind of lines, or sometimes those area. So we see this area, this surface is something of the significant. So when we got, I just put this many of those dots indicating there are certain characteristics or features that is being shown. So let me go to the more of explanation. What is a feature detection? Of course, once you have a feature detected, then it is easy, or it is the next step of matching it with our model and identifying. So that's our image understanding. So process of finding important part of image, that's a feature detection. Then a very important stage when identification area where significant or meaningful components of image are expected to be found. So something important, something worthwhile, something significant is detected. Then there are many different approaches. So it may be just by points or some kind of a region. This is an area. And then this is an edge. So this one is a surface like that one. Then there's a certain edges. So that's a boundary separating out this area and this area. So line, linear, curve, or line can make a separation. Then, of course, a simpler case is a straight line, then that's easy. So in Hoff transformation, there was a Hoff line to detect, or Hoff circle, or Hoff curve to detect it. If in case that you don't know what is a Hoff, then that spells as a H-O-U-G-H, Hoff. That is a person's name, Charles Hoff, and the using from dots to that's a point we have identified or isolated. Then we want to construct the line or curve or circle out of those dots. That was our technique we covered in 4B PowerPoints. So just a little quick review of computer vision steps. That first stage is capturing the image by camera. That's what we did. And in the chapter 1, there are 2 here. The 1 was overviews. So chapter 2, and then pre-processing. So this is very similar to image processing, IP. That is that I said that one time there was a homework that telling what's the difference between computer graphics, image processing, and computer vision. So some people did the good answer, some wasn't very satisfactory. But computer graphics is process of creating, generating image from the data. Then image processing is a process of generating data from image. So you take a picture, then of course that the picture, all it has for the machine, human beings is we recognize what's in there, but for the machine, all it has is pixels. So from the pixel, but of course these pixels are somehow they are changing. The values are changing, so some are red, some are strong, very dark, like that. Those differences or changes are somehow traced, and we create some kind of a data, like there's a lines, there's a points, and there's a certain structures. Those kind of a general idea about and then there was some kind of a noises there, then we filter it out. And if it is too big or unnecessarily they concentrated or grouped in certain location, then we're spreading it out. So rescaling or rotating that can be done. Then some color got a little faded, then we can make it one little reddish color for whatever filter, or because of the light condition, we can move it to quote-unquote normal condition. So that's a preparation stage. Then our chapter 4, we have been talking about the edge detection and constructing those lines or curves from the points, and the discovering or detecting the features, what we are doing now. That one is the next step. So it's the second stage of the computer vision. So computer vision, we said, is the process of understanding the image. So understanding means that when you look at the picture and get the sense out of it, say what kind of picture, what kind of contents does it have, what's the meaning, even you can get some emotional aspect of that picture and some the factual information stored there, that kind of a thing. So that one is what we are talking about. So detecting features is a very important step. So it's a second step after pre-processing. So this is actually IP step in image processing step, but this is a real start of computer vision. Then next goes the constructing object out of those features and get the objects isolated and identified, and then the identifying their relative position. So just identifying that what's in there. There's a tree, there's a house, there's people, there's a car. That's not enough. How they are organized, which one is closer, which one is farther away. That way we understand the meaning of or situation of that picture. That is the next step. Then after that, then you make some kind of adjustment or understanding of motion. We will talk about the motion just a little bit in here, but this is one whole subject by itself. And then reconstruct and get the meaning of the scene or the picture. So that is known as semantics. Semantics is a meaning. So semantic of the picture. So this way we accomplish the goal of understanding. Like human beings, when we are looking at the picture, we get this function right away. Somehow within a split second, our brain just takes care of it, and we right away know that that's the dangerous sign of some cars coming to us, or the house is collapsing, or the rain is heavy, or some very nice friendly face and I feel happy about. Those kind of emotional or the situational understanding of the picture. That's what we are doing with the computer vision. So let the computer do it. Why is it? Because there are cases that we need to look at the pictures and understand the meaning of that or significance of certain things happening, just like the street scene of those automatic surveillance or those watching camera. So we cannot watch every picture. The even more is that when we send the spacecraft to outside with the satellite by, say, the space agency like NASA, then they are just taking pictures every minute and in very fast speed. So they are sending back those huge number of pictures. You know that typically within a day or two, they send 1 petabyte of the images. Petabyte is quite a bit because we have megabytes, and thousands of megabyte is gigabytes, right? And the 1,000 gigabyte is terabyte, and the 1,000 terabyte is 1 petabyte. So it's a huge data size. And the human beings can't do all those reading and understanding, especially like for the military purposes or some the monitoring purposes. So in the case, they let the machine do it. And of course, that's why this field of computer vision has been progressed quite a bit. So here's some example of a scene. This picture shows some kind of a scene. So usually, whether that's a really scenery of natural, the picture, or man-made setting, that usually we call one picture itself, and the whole the understanding of or whole setup is known as a scene, S-C-E-N-E. So here's one scene. Then right away you have the understanding of, okay, here's a tree on nearby to you, and there's houses, and maybe 3 of them. Then there's trees, and when you look very carefully, then there are lampposts, and there's some kind of the rocks in here. If you have enough time to spend, you have a luxury of or need to look at this one for a minute or 2 or even 1 hour, then you may go every detail. But when you have just like 5 seconds or the 10 seconds to look at this picture, then you cannot catch every information in the picture. So what it is that at that moment, even human beings, when they are processing a picture, they have a few features. There's a picture has features, that is a few significant unit or significant the aspects of the picture. So this lamp or the trees of some kind, so we don't know that this kind of a long tree, and houses with windows like that. So frequently when we have no time, not enough time, this window we don't notice, but we just say, oh, there's houses and the trees and the one near the big tree nearby, and it is maybe quite a distance from house to this tree. That kind of thing we have to quickly catch within let's say 5 or 10 seconds. But that's all we do. But the features, what makes a good feature? That's significant, and that's standing out from the background. So here's a sky, and there's a few things. For example, this little trees back there is a little faint and hard to tell the difference from the background. Not that easy. Around in here, if we care to see, looks like there's a cloud. So we didn't notice at the first time, but we looked a little more carefully, and then here's a few things. So this is not a good feature. It's not that sticking out, not that distinguishing. But this tree definitely is a good feature, and this one house is a good feature. Then what we are seeing, when you're looking at the picture, then right away you say, oh, a house and a tree. But come to think of it, when you are like we learn how to understand the picture, then usually our eye goes to the points here, corner of that, and some kind of a linear or some borderline, and then some areas. What kind of material it is, maybe roofing, and what kind of material it is, some kind of rock and some kind of a dirt. So we have that the different aspects of the picture, and some are very easy to detect and significant enough, some are not. So some are good features, some are not so good features. I wouldn't say there's no bad feature, but not as good as some the clear one. And then good features usually distinct, easy to discover and stand out. So it is contrasting, or it is distinguishing from background. So different from surrounding, that is what, and then we say that that's unique. Oh, that's something just by itself. That's the kind of the characteristics we see as a feature. So we need a little more organized way of looking at this, searching for the features, something significant in the picture, so that we can understand the picture better. That's a feature. Is that here one is an area, and one is on this edge or line, and there's a corner. So this kind of name is given. One is the flat region. Region is the area, and typically we have certain the boxes that one makes a window. That is that we see just a portion of them. And so when this window is keep moving around, then that window may be within the area where every element within that element, the window, is all homogeneous, all same. In the case, that's a region. That's a same characteristics. It's a same wall, same roof, same soil, or same part of clothing. So no difference within and a certain area. Of course, we want to maximize our understanding of how big is those region going to be, but we'll do that later. Then our window moves in here. By the way, I'll talk about the window in a minute, but anyway, that when we look at that one, then it turned out to be that within that window, within that the pixel within those box, that there are some distinction. So there's a area, they feature more a flat region, but there is another pixels that's showing clear-cut separation. Different the pixel intensity is different from the background. So this is the line or edge. So sometimes we'll make an edge different from the line here. Edges can be a little curvy, but the line can be straight. Then when we go around it, we may be lucky, or eventually we hit a certain places where it is a point, and that it shows a little more region separation. So within this window, we got 3 separate places, 1, 2, 3 area-wise, and then there's 2 border lines or 2 boundary lines. So that kind of a way that the feature detection is done by area or line or point. So this is the window. That what the window is that in a given house, everybody has a window, and even this room has a window. So what is it? That's the window has a limited area that so outside of the scene, outside of the world is very large and almost limitless. But because the opening of the window has a limit, it's not as big as the nature itself. So we can only see small part of the whole scenery, whole picture. So that's the window. It's more like that when you have in a given paper, thick paper, you have a little cut down this much of a square, well, it can be circular, the hole, and go around it. Then all the other part will be blocked, so you don't see it, but only those open part or that comes within those small opening is something you see. That small opening, small compared to its own, that we say window, and exactly this is what window is. And of course, that depending on where is the window, the people may be standing here, they will see a certain scene around there. When standing on this corner, they may see different area, maybe smaller. If there may be another window in the other wall, and that gives a different scene. Things like that. So the window is a very useful one because we cannot process everything in one time, one small area at a time. That's why we need always working with the window. So we spend quite a bit of time talking about convolution. So convolution, then we had the original main image, and we had a so-called convolute or template or window. That was to make it easy for our life. And we made a 3x3. That's pretty small. And in reality, then maybe the 100 by 100 or 200 by 200, usually square, and that window size can be moving around, and the windows keep moving this one. So each time the window moves, and we see different pixels. So starting whole scene here, and we have a small portion at a time. We are looking at. So that's a moving window. We usually call moving window. So at a given time, that we see only small subset of a total picture. Why? Because we cannot process everything at one time. That's too much. So one thing at a time in a smaller pieces. That is that when you got a huge the meat, like you cooked the one big sheep, and you have only two guys. You cannot eat that. You can eat that. You can eat half a sheep, but you are not going to eat in one gulp like that. But that's rather you'll eat pieces, very much like that. You eat small pieces, and we process our scene in a small pieces for the ease of our processing. Okay. Okay. So in the case, window supposed to move. Keep moving around. So when it is moving in a certain direction, in this direction, that's a vector actually, then it will show different location. How much does it move? That depends. So we have an original location is they look centered at the x and y coordinate. Then we add the u, v, and the v for y, x for. So in x direction, we got a u, and the y direction, we have a v. This is 5 and the 2, or the 10 and the 6, whatever. So we are moving our window. Of course, in general, we are moving systematically, so the small pieces at a time. But in case that we want to make the algorithm more efficient, then instead of moving in small pieces, but rather, say for example, in here, we have windows around in here. Then we know that there are quite a bit of open space that's for the same region. Then you don't have to go one at a time, but you just jump it around and make sure that these are all same the shapes or same the property of the pixel values. So what kind of a change do we have in this window when we are changing from this window to next window? What kind of change do we get? That is then our value will be the x plus u, that's the location, and then y plus v, that's the location, and then we have x and y. So x and y will keep changing within a window, and we are having we have a x amount of pixels and y amount of pixels. We are just having every the pixel value. So here's one window 1, and then somehow then moved to say I make a different window 2. So this difference is u and v, and those things are that this one times this one and this one and that. So when this is original location, this is a new location, then for every pixel, the value of the difference, how much different do we get? How much different do we get? Is that this pixel value minus that? So that difference, that can be negative or positive. So we want to do the squaring. And then y, so we have this value, difference, and squared. So when we are moving, it can be sometimes the intensity may be brighter, the big, sometimes small. So this the difference may be positive or negative. But negative or positive, when big, then it is big. That's a big difference. So in the case by squaring it, we make sure everything is positive, and also we magnify so that we can distinguish more of the differences. So that's how we are detecting the differences from one window contents to next window's contents. Okay, so in page 182 of Zelsky's book, that we see this kind of a picture. So the feature-wise, I'll delete my picture here. There's we can the feature points. They can be points. So when maybe we are this little windows keep moving, and we are identifying those places where there is a point. So we are moving until we find something that is a point. The point means that it is bordered by two borderlines. So starting or the joining point of two borderlines. Like that, this may be like that, sideways, that's the point. So that point, that is unique in that there's some area and another area, two separate areas, and with a couple of, sometimes more than two boundaries. That is our point. Then maybe our window, there's a little bit of window here, maybe some areas like that, so different color, different shape. So this is even circle. So we are not identifying it as a circle, but we say this is a region, this is a region, this is a region. So we just say a sequence of the regions, and eventually the by is a boundary shape or the change of those boundary location will identify it as a circle or some kind of a curve or ellipses like that. And then this may be the another example of a big letter. So this is a region and the whole, region and the whole. So by those the pattern of those movement that we can identify as one letter as a B, the bluma, whatever that, bluna maybe. That's the lettering there. Then here, edge is well. Let's go to the line first. So line is definitely one with a. You said that's just a red color here. Actually, when you run some sample program of the half the line, then it detects the line. Except that it doesn't detect every line, but just the major important ones, depending on the parameter you set it up. So they will be drawn as a straight line in red or the blue, whatever your color. Here, red color. So there's a line there, then they are identifying it as the line. Then here's a line, here's a line, here's a line, like that. So line is easy. So you can go straight to one direction, just have to know where to start and where to end. On the other hand, that our life or most of the objects are so complex, so it's not the straight lines, but there's a lot of curve, and there's the structure within the substructure, enclosure within an enclosure, like a human face has a portion of eyes and the nose is like that. So those things can be identified through the edges. So edges are the general case of those some kind of linear geometric property that separates out two different regions. On the other hand, that if those the linear the edges when go in a straight line, then we say this is a line. So this is again the border line. So equation wise, the line is easier, y equals mx plus b, like that. Also there's just one there's the linear the relationship we can expect, but this one is much more complicated. So typically use the parametric equation where we use something like a t. So just don't worry about it, but x can be the a1 t cube plus b1t squared plus c1t plus d1. So this one, 0, there's no power. There's a first power t and t squared, second power, third power. Anything with a third power that has this kind of a curve, so that can represent the general case. How about the t fourth? Of course, but that will go like that. But in computer graphics or in computer vision, then we are not going to go to that. Then in the case we need P5, P6, that's too much. So rather we separate out at the maximum of this curvature like that. That's a cube stage. So it's called a bicubic. Bicubic is x and y, but are different. So bicubic curve generating. So line is a cubic curve, and I'm sorry, edge is the cubic curve, and then the line is the one-dimensional linear line or linear equation. Of course, that linear equation is a special case of an edge where t cube and t square, those terms are all zeros. Then once we have detected those features like those points and those lines here, and we detect those general area or general area, there's a region here, then even if that this is the same one, but it's definitely the orientation is different. It's you take a picture from this angle and you go to sideways and took another picture. So that case, then we see that we can make matches from here to that, and that one for that, and that line as that, like that kind of a correspondence we can get. So let's see how they are doing. In here, that with the here there's a well, there are many features it has been identified, but there's one point. This one is point, and this is a region, and this is a line. So if you just isolate those portions only, then that's more like that. So we have a little bit of bump here, so that's a point. Then this one is an edge here, so rock and the snow separated it out. And then this one is a general area of the sky, so all homogeneous, all same within. And then once we have that, then we can get around and check there's a feature. Oh, there's a point, there's a point, there's a point. So you collect those point feature and see, okay, here's one feature. So turn out to be there are many. This one matches. It's easy to find the match in a smaller scale rather than big one. So they say, that matches. And then here, this portion, that one is more like that, like within the window that there's an upper part, or some part is dark and the other part is light, and the light part is larger than dark part. So this one matches. And then the sky, the all blue, here this blue and this blue, slightly different blue, but nevertheless that's a match, good match enough. It's much like when you are looking for the fingerprint match, then there's loops and hoops like that, all those loops. We'll look at that one in a minute. So in that case, that what they do is in the court or in the police, when they find 13, depending on the country, when you see 13 points of similarity or matching, then say that's the same. You don't have to match everything perfectly. So because of the fingerprint is so much diverse from one person to other, so it is not that the 13 match is not by chance, but usually by make sure that this is a reality. So that's how it goes. So whether those matches can be given. Then same thing goes with this this house, one little hut is called that. Those different matching. So again, that this one is a region. This one is a boundary, more like, or it can be a point actually for this one. So it's a point, and then this is a line boundary, and then here's the boundaries, and some another boundaries, or it can be this one as a point, and this is a region. So we can get the matching of that region and that the point location, and those lines here, and those lines here, and then more of a points in here, this corner points. Those things are matching. So with that, you say, okay, turn out to be that this picture and this picture is the same. Once you got the same, of course, we need the original database. Maybe this is in the database. So when you get certain picture like this, then they do the matching and say, these two structure is the same thing. So you can say that. Another way is that the image matched by region. So in here we have this much of this. This is a book, and then there's a window size like that. Within a window, a large window, there's two eyes. So there's a center of this a bigger eye, and from there, right angle, the showing the size of a smaller one, and then the relative the intensity there. So once we got this kind of thing as characterized, then the book is laying down in here. So we know that this is a multiple view geometry, same book, but this one, this picture window and this window is quite a bit different, but nevertheless, we can say that by rotating around, they go around a little bit like that and shrinking a bit and slightly changing its angle, that we can say, these two are same. So that's the matching. So matching is very important in understanding the picture. So we are matching faces, we are matching fingerprints, we are matching our scenery and the letters. That's how they recognize the letters by machine. So one method they are using, there are many things done at the same time, but you pixelize. Pixelize means that you make the averaging of the regions. So this is a fairly large window, and then you are making a large chunk here, and you average all the pixel value, including the color. So we see that this portion of the brown portion of the other eye is boils down to this, and then this location of a general the blank or the no objects can be more like that. The center of those eye can be around in here. Then this part may be over here, and then this part may be over here. Things like that. So, and this may be this part. So you can make those distinction. So this corner for the match, this corner for this match, and then that corner for that match. This original one like that match, and in between there is the blank space, and then this corner is matching with this. So once we have those, then we have this picture and cut up with all different the samples, and eventually we see that this pattern and this pattern is very same. So this one we are matching it. So that's how it goes. Something very important though is that there won't be this two, even this kind of approximation. There's no 100% match. That's not easy. So what they do typically, like 80% match may be good enough, or 75% may be tolerable, like that one. Statistician won't say 95% is the same as 100%, but in reality or in practical, the application, that is a little too big. So this is an edge finding algorithm. So I don't want to go to all the detail, but what you do is that you keep just moving, and if this intensity value is above those differences, the certain T is a threshold. So threshold is in a given house that there's a little bit of a structure that separating two rooms. That is usually called threshold. So in this case, that you say that there's a certain, this is more like this area separation. So you make those certain values, intensity, and if that intensity value is larger than certain the tolerable range, then you say this is the different. So that by the judgment of the threshold, you are saying that here is some kind of edge here. So you keep going, the windows moving from here to here slowly bit, and there is a certain places where there's the change is too much. Then in that case we say, this is the edge. That's more or less of that one. So you do keep how many edges, another edges, another edges. K is the edge, the ID, identifier, and that can be increasing. So in a given picture, there may be 10 different edges, or 400 edges, or just 2 edges like that. You can find it. And then region can be growing. So in other words, that there's a partial border. So to identify this is our big region of same nature. So same wall or same desktop or sky like that. Then here is the algorithm, that pixel array algorithm. So you keep just the border pixel for each border pixel here. That you just look at the intensity and see until it hits the other side of the opposite edge pixels. So what it is more like you are searching and moving until you hit the other end, and moving until you the other end. So within that, you recorded how many pixels you have traveled. So those areas will be, initially there was only 2 pixels, there's 4 pixels, and the 10, 20, 30, 40, like that. That the number of pixels will be increasing as the area widens. So those things are recorded in your database, and you get the idea about where is the region. And this is another one. I was thinking about using this one as a blob coloring. That is that, suppose that we have identified all those edges. So we begin with the picture that got the all skeletonized. In other words, that all just thinned out with those border lines. So we got the border, then we got the count. Where is the region? I mean, how many different regions there is. That's the idea. So one method, so this one is more like a binary, 0 or 1. So in the case that if it is 1, that means in the edge. And if it is 0, then that's the area. So you just go, you start going on, and it's a region maybe 1. Then suddenly, oh, I hit the boundary. Then this one will put that one as a, because we go on, this is a 1 because it's a boundary. Then in the case, we will see which above and the low pixels. So look at here, that we have a triangular, we are looking at 3 pixels together. 3 pixels. So this is current pixel. And we are going left to the right and top to bottom. And this one is a pixel value x of upper and pixel of left. We are moving left to the right, top to bottom. So each time we are looking at that the pixel above and the pixel left and this one pixel current. So we moving it, then we are making the comparison with the pixel above and one just we left. This may be 0, meaning that it is a part of a region. So if that's the case, then this one, whether it's regardless of this value, this one is not a part of a boundary. Definitely current the pixel is. That is that we went on and our current pixel is not a boundary. That's what it means. X equals not a boundary. Then no action, just move on, keep moving on. But turn out to be this is all the rest of them is that the current one is a boundary as a 1. So okay, this is a boundary. And then look at the up and the down. Then above 1 and below 1 is all non-boundary. That is very much like a situation maybe somewhere around in here. Yeah, this one, like that. Then if you have a one point like that, then one above and one left, those things are both zeros, right? So in the case this one is a part of this location of there's no boundaries. So I'm starting new boundary. That's what it is thinking. On the other hand, that when one on the left is boundary, and then current one is a boundary also, then this is a boundary. One on the left is boundary, mine is boundary. So it's much like I'm continuation of this line. So I'll continue on with the left one, or above one. So in this case, that the left one, this is above, I'm sorry. So one above, current one is a line, and above is the line. Then we'll just go ahead and follow. My new line is the same as one above. So it is more like going along those lines. And the one on the left is above is 0, but one on the right is 1. Then it's much like we are going along this. So this one is another boundary, but current one, previous one was a boundary. So this one is the same boundary. So it can be either line going down or going sideways, and that then those previous the above or the left or horizontal or vertical line is part of the line I'm going through as an edge. That's what we are doing. So same thing, and then they both the above and the bottom is all one. There's a boundary, and this is also boundary. Then there's a new part that I got to start. So this is the new line, this is the new line, the boundary, this is boundary. I am in the boundary. So then maybe a corner. So the region-wise that I am in the boundary of the two branching out, two boundaries are branching out. So that kind of idea. So once we follow this one, this is very simple logic, then you can just do the painting. So 3 will be all painted the same color, and then this is different region 1. So 1, 2, 3, 4. As that we keep getting increasing the region number. So time goes in, then the region number will keep increase. That's how it goes. This is then template matching, simple template matching, easiest way. So we said that here's a template here, and this is what we do in the exercise 1 in the lab. So what you do is you superimpose that one over here. So 1 for 1, 1 for 1. Actually, this is quite unique. The special cases for in here, this is an industrial machinery or surface of that, and want to match with those nuts and bolts. So sometimes it's very shiny and it's dark, so it's higher and the lower intensity. So intensity maybe not be just a binary. The one in the exercise in the lab, I just made it everything 1 was 0, but it can be higher intensity in here. So what you do is that to see the match, that 1, 1, 1, 1, 1, 1, we have a 1 times 1 plus 1 times 1 plus. So every member is multiplied by the position that we call that convolution. So for example, for this one, because everything is 1, 1, 1, we know that this is matching, this is matching. Out of 9, 7 are matches, just adding. So that's the 7 in here. Then if we move around in here let me change the color into different color. That's not very easy to. So I'll give you this color. This is 3 by 3, the matrix, the 1, 0, 0, 1, 1, 0, 0, 1, 0. So obviously it is 4 4 is a matching with the 1, 1. 0 times 1 is 0, and the 1, 1 like that. So the one more time that we go with this one. So 0, 0, 0, 1, 0, 0, 1, 0, 0, then only 2 matches. So that kind of numbers. Then the on here, the one the high value is here. That is this 9. So you say why this? It is all nothing but this 1 and times 1, and this 1 times 8. So you add to 9. So this highest idea is that if template has a brighter part right in here, somehow the location has those brighter part. So that give higher the credit of intensity. That's the way to do the matching. So this can be used. Actually, I have this the page twice. So one way down near the end of this PowerPoint has the same page. But to align on image, we can use this matching and the three-dimensional the objects or three-dimensional data reconstruction or motion detection or tracking that be used for those kind of template or this feature matching. What's motion is that we know that certain objects are moving. So in a picture that we want to know which feature is actually moving. So motion detection tracking is very useful for that feature, the detection and the recognition, of course, and the indexing and the database retrieval and the navigation. Robot knows that, oh, there's a table, I must go around it. And if there's a little bit of a rock in here, then I'll just jump it over instead of just passing through like that. So the navigation of the robots are done for that purpose. So actually, computer vision, CV, sometimes called the machine vision. So actually, when I started teaching this the computer vision, then the many books they had the title machine vision, and even some of them has a robot vision, so robotics. So, but it's more focused on robots. So it's slightly different. So let's look at those idea about the motion detection. That's easy. That this picture and this picture they are same. So the camera is stationary, meaning it doesn't change. What's changing is that time. So this is time t equals 0, and say t equals say 1. I don't know what is 1. It's 1 second later or 10 seconds later. So we see that what just by they're looking at, then this car is moving, and the rest of them seem to be exactly same. So what we do is that all you have to do is that you subtract this picture, that's the second one, and then minus this t. So original one minus so new one minus original one. Then something that didn't change, this thing that didn't change will be subtracted out, so will be completely dark. Then this car, this one, all those the road line is all 0. I mean, they all same, so subtracted, and the 0 value that is dark, like this dark. But something changing. So this one, original there was this car, but now that subtracting is that this be subtracted. So this location has some differences about one unit and another unit still standing with the different colors. So here by proper, that this one is a little looking funny, but this can give you some clue about what has been changed. This is a better picture. Here's one scene and another scene, and we see that this car is moving. So subtracting it, then we clearly see these pictures of the car. Then funny thing is that there are a few minor things that's been changed. So is that some kind of the other objects moving or some human beings walking, we are not sure. So this resolution isn't good enough. But by subtracting from one scene to the next scene, anything that's changed will be showing up. So I think I didn't say that about MP4 format. That's very popular, or maybe most popular video format. The reason why it is popular is that it saves, it takes a small, the minimum space. The reason why MP4 is the useful, or the saving space, is that it gives the original picture in the full pixel value. But next one, that anything that didn't change doesn't give any value, except that we say that those things has been changed. So they used to be this one, but now it is changed with this value, and this one, and change this value. Only those changes will be recorded. So there's a method of encoding. So it's more like it says, well, up to this much. So suppose that one is, suppose we have a 1000 pixel, and then this is a 200 pixel long. There's absolutely nothing changed. Then up to this much. So this is another like 100 the pixel long. There's no changes. Then that means that we got a 1000 and a 200. And 100, so that's the 20,000 pixel plus there's 100, 200, 300 more. Say just a number fabricated. That the code says 20,300 pixels will be black. So, well, actually, unless there's some other coding. So after this number, then there's a little bit of the marker, and then say it is a black. So meaning that there's all blank, there's no changes. So when it is and then after that, there's a 30 pixel that has a value of 20, something like that. This is all 0, I mean, and then 20, 30, 20, and then 10. The 15, like that one. Then next, the 10 pixel has intensity of 10, whatever like that. So what it is reading this data. The system or the software will read this data, and then from previous picture, you just make those the modifications. So one is 0, don't do anything, and then after this many of skipping, then give those value change, those pixel value being changed for next 20, 10, 30, like that. Then it'll construct a new next frame. So it sounds tedious, but machine can do much faster than human beings, and that saves a heck of the space requirement or storage space. So what it is that instead of going the whole picture at one time, that we go by smaller pictures at a time. So that's locality, because it's a small subset, so it's a local. But the good thing about the local features is that the locality that gives much more the robust, meaning it's more the fixed and the much kind of strong indication. So the locality makes it much more reliable, and then the distinctiveness, so it can differentiate the large database, and then the quantity was hundreds of thousands of a single image can be processed with those locality. So it's faster, and it can be used for any kind of picture. That kind of advantage is existing. So in here, local features wise, that this portion being recorded as that, this portion as that. So those local features are pieces of data being used for the matching and the kind of characterization of new pictures for the combination. But important thing is this invariance. Invariance means that doesn't change In means not, and the variant. So something we standardize it so they don't change. It's more like a template, and we can use it when doing the matching, slightly differing it. So it's much like the engineers using the tool, like a flex tool. So this is original shape like that. Then there's a way that you can increase a bit or shrink a little bit and do the matching. So once we have that, then it's easier to match. So here's this portion, that portion, and that portion being matching together, like that one. So the local features, but that's standardized. So this is a feature description, and this become invariant. This is a fixed. Then when you're doing picture comparing, then make it smaller, or make it rotated, make it moved. That kind of a change, so-called geometric transformation you can generate. So here comes that the issue about those invariant. So fix it or not changing. That's our key issue here. So the guy named Leonhard Euler, who is the mathematician from Switzerland, who did the research. Actually, Euler is the person who have invented so much of the mathematics. So all your symbols like the plus, minus, multiplication, division, square root, and then sine, cosine, and the inverse, and the integration and the summation. All those symbols and concepts were invented, or in a way researched and published by Euler. Not it's a Euler, it's a Euler. It's a German way of pronouncing his name. The word Eigen was used by Hilbert. He's another very famous German mathematician, and he said, okay, then can we create certain kind of a value that's unique and not changing, so-called invariant the property we can generate. Then not only that, in doing so, you can create some kind of a data reduction, meaning that this is our data. Typically, our data is two-dimensional. So the description of many values by time and by location and the colors. So this one is eye, and the eye size, the color, and the length, and the intensity, what is that, the diameter of pupil, whatever like that. So it's for eye and the nose, and the left eye, right eye, we can have, and the lip and the ear, like that. We got a whole bunch, and we can match up total numbers into square. But it's a huge data. So anyway, this is a large. Well, we have only here 6 by 6, but very frequently it can be 100 by 100 or 1,000 by 1,000. So 1 million the points. So for every member, we have one big chunk of data to use. That's too big. And also it's varying. A little bit of changes can make a whole thing just they messed up, or just they change the whole bit. So somehow, can we find or reduce this one into one vector, one row? Here's many rows and one column, many columns, 6 rows, 6 columns. So just make it one column data reduced, and one more data very much like that. That has been what we are talking about as eigenvalue, eigenvector, like that. So eigen again is that one, uniqueness. In German, one is ein, E-I-N. But the eigen is a oneness, that kind of meaning, eigen. So single, unique, its own. It belongs to that person or individual, nobody else. That's the idea about those eigen. So can we reduce our data, this large data, that's a two-dimensional, into one-dimensional vector and one value? and use either this vector or this single value as characterizing or representing the invariant description of that object or that person. So later on we'll talk about eigenface. So the face has a lot of features, and that can be in a large 2x2 matrix. Can we make into the matrix? And if lucky, then can we have one value, 317.1475 so like a very lengthy, because everybody's face is different. So to characterize or represent one person's face in one number, we got to have a distinction of a whole world. Got right now like 70 million people, and then no reason that every number must be in sequence. So we got to have a very high precision. So far, then instead of that, let's use this vector. So very long vector, but nevertheless it's much better than whole matrix. So idea is that having the kind of a relationship. This is what Euler proposed, and also Hilbert's that he did also. Let me go to a different color. So A is our matrix 2x2. Then V is a vector V. So somehow can you find a vector and one scalar, that's one number, such a way that this matrix times this vector has the same value as this single value and this vector. So this vector is very important, obviously. So if we can find it, then we can use just the V and the lambda for some kind of a helper. So our vector will be very much useful for characterizing one element, or rather this A become one vector. So our saving is great. Like we said, 1,000 by 1,000, then it's 1 million elements. Now become just 1,000 elements, no problem. And eventually comes with a single value. So the example goes very much like that. I'm sure that hopefully you know how to do the matrix multiplication. We did that already. So 3, 2, 3 minus 2 times 2 and 1. This is we have derived. So don't ask how you got it. But 3, 2, 3 minus 2 is our original data. And somehow by magically we got 2, 1, and 4. So 3 times, the way it goes is this times that plus this times that is our first elements. So 3 times 2 is 6 plus 2, so that is 8, isn't it? Or let me write it, 6 plus 2. And then 3 times 2, that's 6. And minus 2 times 1, that's minus 1. Minus 2, I'm sorry. So this become 8 and 4, isn't it? So this is our vector. So the A times V is 8, 4. Is the same as lambda and V? Okay, V, lambda, same thing. But V is the scalar. So vector was 2 and 1. So and the lambda was 4. So 4 times 2, 4 times 1. So there's 8, 4. Same. So this is very simple. So it sounds too easy. But if it goes by 10 by 10 matrix to eigenvalue, eigenvector, it's going to be much more challenging. But anyway, somehow we can use from now on, instead of this vector matrix, this two-dimensional matrix, we can just use this vector. That's all we have to worry about. So invariant character of an object can be represented by eigenvalue and the eigenvector. So as I say, that when the very large, there's a lambda, that is eigenvalue, this value becomes very complicated form, and this is one unique form. So one fingerprint can be represented by a single value instead of a huge 100 by 100 matrix. So just one more time, that this one is something I want you to really know it. Memorizing is easy, but just understand this. Big matrix, two-dimensional, and this is one-dimensional, 1D. So we have from 2 dimension to 1 dimension to 0 dimension. That's one vector, single value. That value. That's another vector. Lambda is a single value. Like in previous case, that lambda was 4, and then our v was 2 and 1. So just one vector. Then original value or original data was that the 6 2 minus 2, something like that. Anyway, we got a 2 by 2 matrix here, and here's a matrix here. So this is a matrix and the single value and the single vector. So it's a much better deal to have these vectors being used. That's the idea. So here's the way to go is that you are subtracting this is calculating determinant, so minus delta, and then you can calculate this the vector. We'll do this exercise of the deriving eigenvalue and eigenvector. That if it's the more than 3 by 3, it's going to be too complicated. So I just want to give you some idea. So again, there will be practically no chance for you to actually derive this eigenvalue or eigenvector, but just to know that using this mathematics, that we are making those huge data, like 1,000 by 1,000, is reduced to just the same without losing the uniqueness. Maybe all the detail may be lost, but uniqueness, because all we are worrying about is the comparison, just 1,000, so 1 by 1,000, and then there's a single value, 3.1456. So this is Taylor sequence. They actually, when this is a huge matrix like 1,000 by 1,000, you need some kind of a Taylor sequence of a numerical method and the partial derivatives, and you can calculate those changes or differences pretty easily. So in here, that by using the feature can be detected. Feature can be detected either the edges or points or the area by using those characteristic values. And it's the same idea as before, of that those differences to generate, and you square it so that difference is being squared and everything become positive, and also the size difference or difference sizes being squared, so it's easier to compare. So this is the same idea, that the feature detection wise, that you end up getting this matrix, but you have original data, the pixel location and the new pixel location, and then this invariant vector as a kind of this major matrix to calculate. So u and here and the u, so you have a u squared somewhere and the v squared somewhere, and those compound form. So they have edge detected and the direction of where does it go being they also detected. So the calculating eigenvalue, eigenvector, that one I just did it. So to calculate it, then you need the determinant. This is something that I'm going to talk about in the lab session next time, and then by doing so you can calculate. So again, I want you to know about this eigenvalue and eigenvector and this meaning and this purpose, and why it is widely used in mathematics, statistics, and in AI and computer vision. So this is where the things are being used, eigenvalue being geometric transformation, molecular biology, and geology. Glaciology is that the iceberg, the shape and this movement, and the vibration, and the face recognition by the eigenface, and the graph theory finding the path, and then statistics. So PCA, in the next portion of the lecture, we'll hear about the PCA a lot, principal component analysis. But uniqueness of the certain shape, just briefly, molecular biology, that when you have a headache, then you're eating aspirin, and then these days that they have a cure for COVID virus. How do they do? Actually, our molecule is very much like each protein of our blood, or the skin is very much like that. So they are acting, and especially virus, the cells or virus unit has the outside there looks like this coronavirus has a round ball with a bunch of the spikes, but inside there's a protein, shapes. So the shapes are portion like that. So the shape of this one and some space in between, the wiggling, changing, that causes this one infecting or killing other cell like that. So by proper the researches, then we can get a certain portion of those virus cell or bacteria cells as a certain hole inside here. When I teach bioinformatics, then I could have said more. So anyway, this kind of little thing. So this space is somehow existing all the time. So what you can do is we can create, our drug is nothing but molecule that has shaped like that, and just to plug it in. It's much like a peg. So it's think about that. For example, what could be the one that anybody playing accordion? That goes playing, moving around and around, and then you are making this, the wind and make a sound. But somehow you plug it in something. Or your door or wheel is just turning around, and you plug it in some stick to that, then it will stop. Very much like that. The protein must wiggle and do the work. But over there, you just put this material. That one doesn't change. Then it cannot wiggle or it cannot move anymore. That kind of a special shape is called the ligand. So to find out how the ligand look like, that you can have a so-called feature structures. So that's being used in the drug finding researches and the molecular biology. Then another one, so good thing about this that once we got those characteristic value, so some kind of vector. So this is our eigenvector. Then you can scale easy. So eigenvector is a vector. So if we have eigenvector like eigenvector of the v1, v2 like that, this is x and this is y. So the new x value will be this one times that, and plus this one, next one is this times that, but this is 0. So x equals k v1 and y equals k v2, like that. Then it is increasing or decreasing in equal sizes. That's a scaling of same size, so often called uniform scaling. on the other hand, that we have a different k. This is a 3 and this one is a 4.8, something like that. Then it goes more on the y direction than x. So things like that is different, and the rotation is different. The angle, so new value become the previous. Actually, new the location after rotation is say x prime y prime. Then the equation is x prime is x cosine theta minus y sine theta, and the y prime is x sine theta plus the y cosine theta. So that's what the sine minus and sine cosine cosine. So new location can be calculated very much like that. So well, we have those eigenvector as our characterization of our pattern or feature, and that can be rotated or scaled, or it can be the change in the location. And this one is hyperbolic, the rotation. The hyperbolic rotation is that changing from 2 dimension to 3 dimension, much more complex form. So the Mona Lisa shape is skewed in here. That one, this kind of thing is known as a shear. Shear means that when x prime is because of this, it's the same as x, but y prime is the y plus then a, well, here's kx, isn't it? K times x and y. So what does that do is that as x increases, y increases more. So this one is actually horizontal skew. So as we increase the x, then y value is increasing to a certain direction. So it's just kind of slanting. So if a square like that become square like that, that is our shear, the operation. So that can be done, or as soon as you got eigenvector, you just multiply this 2 by 2 matrix, and then you can get any kind of a shape changes be made. So isn't it nice that you can make original shape and that just being changed by this multiplying with this matrix? That doesn't take very long. Okay. And the good application is eigenfaces. That's the subject of next lecture part. So next lecture will start from eigenface aspect. So I'll stop in here. This is the catch up. One more thing to talk about is that the handout I gave you last Thursday, that in the second page of those checking for the eigenvalue, vector, I said, oh, I made a mistake, but actually there's no mistake. Everything is just perfectly right. I was pretty much tired, so I just said this, I somehow confused. So when you got the time, please, whether you have time or not, try finish up page 1 and 2 of previous handout, then we'll complete the third page next Thursday. Okay, that's all. We have 1.5 hours of the class. I know you cannot ask questions, so I'll just stop in here and just hopefully that this gives you some understanding of the this features and the usage and how the eigenvalue, eigenvector being useful. Just the one thing to say is that the faces, this one, face data can be a vector, matrix, two-dimensional matrix. But this one reduced into some kind of a vector, then vector can be, all the detail is lost, but at least the uniqueness of an individual face is captured and can be reprinted very much like that. And here very much like that. So using that, this face become to that, then you can identify different face and uniquely make a distinction from one face to other. Okay, that's all for this part. So we'll see you next Thursday. Bye.